Okay, so here's the problem we're going to do today. We're going to do, let's see. We want to solve this. Now, technically, we could try to do the system of equations that we solved using the elimination method, but the problem is there's 3 here and there's 3 unknowns, so that would be really, really difficult, and it would require a lot of algebraic steps. It's not that it's wrong, it would be highly inefficient. So we're going to do the eigenvalue, eigenvector approach that we did last day. I'm going to shortcut a lot of the linear algebra steps because our goal is not to diagonalize a matrix. Our goal is to simply come up with the solution. So there's a lot of in-between that we will do in a Math 254 that's really necessary for our goals in that class, but not necessary for our goals in this class, which is simply, let's get the answer. So the diagonalization process, which is huge, that's where you're finding your P and your P inverse and you're doing all this stuff. We actually don't need all of that for our goals. We do need that for other things. And so it's still a valid thing. So the first thing we want to do is write this as a matrix product. So we will write it as dy1 dt, dy2 dt, dy3 dt equals 1, 2, 2, 2, 1, 2, 2, 2, 1, y1, y2, y3. We will call this the y prime vector. We'll call this matrix A, and we'll call this the y vector. So our goal, in the big picture, our goal is to diagonalize A. But the more simple goal is to find the eigenvalues and eigenvectors associated with A. Now, the eigenvalues, we don't have any control over. They are what they are. The eigenvectors, because we are going to parameterize things, there's an infinite number of variations that are correct, but there's generally a most efficient. Everybody okay with that? There's usually a most efficient answer to any given question. So we're going to start with this problem right here. We're going to do a minus lambda I, the determinant equals 0. And that will allow us to find the eigenvalues. So when we do this, we're going to have 1 minus lambda, 2, 2, 2, 1 minus lambda, 2, 2, 2, 1 minus lambda. Now, as most of you know, because you've had linear algebra, when it comes to evaluating a determinant, especially one that's bigger than, at least 3 by 3 or bigger, you can do row or column operations to put zeros in, and it often makes it faster. If I had a 5 by 5 determinant, I'm going to do tons of row column operations to get it down to just 1 or 2 steps. But the problem is any row or column operations I do to put zeros will just make it more complicated because of the lambdas. So you really can't do any simplification. There's no trick. For example, it would be so much easier if I had zeros here and here, but in order to do that, I would make these 2 rows so much more complicated, it's not worth it. So we're just going to take this as is. I generally, unless I have a 0 in the problem, I usually just always go first row. If I have a 0 in there, then obviously you pick the row or column that has the 0 because you've minimized the work. So this is going to be 1 minus lambda times the determinant of its minor. That's what this is called. Then minus 2 times 2, 2, 2, 1 minus lambda, and then plus 2, 2, 1 minus lambda, 2, 2. Okay? This is the expansion by minors. Does anybody remember what a minor is? When you use the term? If you pick any position in any determinant or matrix, it would be the same if I was using the matrix. The minor is what's left when you block off that row and that column. So every one of these has a 2 by 2 minor associated. That's the reason, namely, and I do a formal proof in linear, why it does not matter what row or column you choose, you will always get the same final answer because every number is eventually used in some capacity. So when I do this, I'm going to get 1 minus lambda. Now, 2 by 2s are easy, right? So let's go ahead and multiply that. So it'd be 1 minus 2 lambda plus lambda squared minus 4 minus 2 times 2 minus 2 lambda minus 4, and then plus 2 times 4 minus 2, so then be plus 2 lambda. Does that look about right?
Yeah.
Okay, you cannot have errors. Errors no work. Okay, so let's clean this up. So this is going to be 1 minus lambda, lambda squared minus 2 lambda minus 3, minus 2 times negative 2 lambda minus 2, and then plus 2 times 2 lambda plus 2. Now, at this point, normally you would distribute, gather all the terms, and then you'd have a third degree polynomial in lambda, which I don't really want to factor because that would mean that I have to factor a cubic, so now you have to use rational root theorems, look at the last coefficient. Might be easy, might not be. If my constant term was a 0, then this would be an easy factorization. My constant term is going to be negative 3 plus 4 plus 4. That's not 0. That means I actually have to factor a cubic, and that is not easy. So what I do in linear, and I've taught this for years and years and years, there's an easy way. And it starts right here. Don't distribute. Nope. What's this going to be? Plus 1 minus 3? Do you notice anything? You notice anything?
Negative 1 is the root.
Well, but I still need to factor everything. I have a common factor. I didn't distribute because I know I'm going to have a common factor. You're always going to have a common factor? Actually, yes. It might not be apparent from the first row. It might have required a different row or column. My experience is the vast majority of the time, if there's a common factor, you will see it. And when there's not a common factor, often distributing it won't matter because maybe your constant term is a 0 or a 1, in which case factoring the cubics now really not that bad. This is under the assumption that you're getting rational roots. And rational roots in this sense means actually integer roots. Why? Because the coefficient on lambda is always going to be a 1 or a negative 1. So you're not ever going to get fractional answers. You're either going to get integers or you're going to get ugly irrational answers. But you're not going to get fractions. So if I factor this, the common factor is lambda plus 1. So what does that leave me with? 1 minus lambda times lambda minus 3 plus 4 plus 4. That's just a quadratic. So let's finish that. I'll do it over off to the side. So if I distribute, I'm going to get lambda minus 3 plus lambda squared plus 3 lambda plus 8. Hold on, that's not quite right. Minus lambda squared. Does that look right now?
Yeah.
Okay, so that's negative lambda squared plus 4 lambda plus 5. Or how about the negative of lambda squared minus 4 lambda minus 5? That might be more useful. Does that factor?
Yeah.
If it doesn't, we're not in trouble, it's just not as fun. How about lambda plus 1, lambda minus 5? Oh, so what does that make this? That's called the characteristic polynomial. Now it's called the characteristic equation. There's a distinction because one's an equation, one's not. I need to solve the characteristic equation, and I did it by factoring the characteristic polynomial. So do we have nice lambdas, well-behaved lambdas? It's a yes, but.
Negative 1 and 5, and there's multiplicity.
I have multiplicity. That means there is no guarantee. There is no guarantee because of the multiplicity. So up top, I'm going to write lambda 1 equals negative 1 with multiplicity 2, and lambda 2 is positive 5. The problem's only going to work if the eigenvalue with multiplicity produces that many linearly independent eigenvectors. Or in other words, if the dimension of the eigenspace associated with this guy is 2. Now, you notice anything about this matrix?
It's symmetric.
I chose that on purpose. A symmetric matrix is always diagonalizable. I will always get n linearly independent eigenvectors, even if I have repeats. I chose that one on purpose. That's a fact that you may or may not remember from linear algebra, and it does not in any way influence your strategy, by the way. I just chose it because that way I know it's going to work. There's no guarantee that an eigenvalue with multiplicity is going to produce enough eigenvectors. And you're rarely ever going to see multiplicity 3. It would be really hard for me to design a problem like that, other than using the identity matrix or the zero matrix. The identity matrix, you have one eigenvalue with multiplicity. The eigenvalue is 1, and it repeats itself n times. And the zero matrix, your eigenvalue is 0, and it repeats itself n times. And both of them have n linearly independent eigenvectors, strangely enough. Then they turn out to be the standard basis. But that's the exception. So let's start with this guy. So we want to do a minus lambda I, so it's a plus I. And I often write it like this, augmented with zeros. That just allows me to go right to the matrix that has the column of zeros. Remember what we said last day. It's a minus lambda I times the vector x gives me the 0 vector, and then I set it up. If I write it like this, then I can go right to, now I'm adding 1 to the main diagonal, aren't I? The column of zeros is necessary because you cannot parameterize just a matrix. You can only parameterize a system of equations. There's no equations if I don't have the zeros here. I think this one's going to work very nicely. Aren't I going to get, by taking negative row 1 and adding it to row 2, negative row 1 adding it to row 3?
I'm sorry, I kind of lost you. So you're using lambda, you're using the first eigenvalue, -1 for, in this equation, which
So
becomes
it's always
a
a
plus
minus
I.
lambda I.
Right, which becomes a plus I, and then the colon, sorry, that's the port. That's
And I'm augmenting it with zeros.
Oh, okay.
That's the same as saying I'm doing this. And now I'm going to do this as a matrix equation. So I take this matrix and I augment it with that column.
Thank you.
I'm just saving myself a step. Once I do this process a couple of times in a regular class, then I just go to here because everyone realizes this was our ultimate goal, was to get to this. And we can start with this. We don't have to get here I state it, I do it, okay? Now, tell me about the parameterization for this one.
Just 1
I have one equation,
and 2 unknowns.
but I have 3 unknowns. X1, call your unknowns X1, X2, X3. So what does that mean?
You need 2 parameters.
2 parameters. It's the difference. Before, right, we had a row of zeros and we had 2 unknowns. There was 1 parameter. Now I have 2 rows of zeros, but I have 3 unknowns. It's not the rows of zeros. It's the difference of the 2. Just for fun, I mean, I could keep going 2, 2, 2 forever and ever and ever, couldn't I? And I'd have a lot of rows of zeros. But it's still the difference between 1 equation, 3 unknowns, 2 parameters. It never matters which ones you choose, but if it doesn't matter, I usually choose the last 2. So I'll say, let's let x2 equal s and x3 equal t, so that's s. Then what's x1?
Negative 2 minus t.
Minus t. Beautiful. So we start by saying any vector of the form, and now we're going to manipulate this. What we did last day was, because we only had 1 parameter, we factored it out. Can I break this into 2 vectors? How about I do this? What would the next one be?
Oh.
You remember doing that step? So if I distribute and I add them back up again, I'll get to this. So I have a linear combination of these 2 vectors where s and t represent any real numbers, including 0, which is important because The zero vector has to work. This is not a vector space if the zero vector isn't in it. Do you agree with that? I would have no additive identity. No, we're going to check in a moment. We're not ready to check yet. Yeah, John?
How did you get negative s minus t?
Oh, because if, just go, what does this say? This says 2x1 plus 2x2 plus 2x3 equals 0. So if I pick x2 to be s and x3 to be t, think about throwing those on the other side.
Okay.
And then I would get this.
Okay, the 2's cancel out. So like it'd be 2s minus 2t
It'd be
equals 2
negative
x1.
2s minus 2t equals 2 times x1. So
Okay.
we could have taken 2 steps and made this 1, 1, 1, 0, and then do that. Then it would have been 1, 1, 1. But it's the same. I'm lazy.
Okay.
It wasn't going to change anything. I would have had to write an entire another matrix though, and I don't know. I just don't have that much energy. You know, I'm getting old. Okay. So what are we going to choose as our eigenvectors? And it's actually a choice. I'm going to choose my first eigenvector to be negative 1, 1, 0, and my second eigenvector to be negative 1, 0, 1. This is a choice. I'm pretty sure I did it right. So you guys okay with that? I can move on now? I'm pretty sure.
Question. I just want to make sure when you're choosing, and you have, let's say you have more than this, or do you just choose, like how do
You
you know
have
which
one
you
choice
want?
and one choice only. You're choosing the basis of the eigenspace. In this case, the basis has 2 vectors. There is no other possibility for a choice. So when a book says, well, choose values for s and t. No, that is not allowed. That is the one thing you cannot do, because you should always choose 0 if you're allowed to choose. Remember when you get to choose your arbitrary constant in finding an integrating factor? Any real number would work, so you chose 0. If you get to choose, then you can choose things that won't work. No. People will just always choose 1. Why? Why would you choose 1? What if it made more sense to choose a half, or 2, or something? No, because sometimes these would be fractional. No, you just pick the basis of your eigenspace, which is this vector and this vector, because every linear combination of these 2 vectors, or the span of these 2 vectors, is the eigenspace. Boom. So I'm picking these 2 guys. By the way, any scalar multiple or any linear combination would also work. So when I go to check it, I'm going to go right to here. I'm going to kind of, I don't need this anymore. Agreed? So, in fact, I don't need this. Okay, I need the space more than anything else. So what I'm going to do,
Question.
yeah, I had an orange pen, I thought. Oh, yeah, I do. I still do.
When you were saying, I'm pretty sure, are we good with that? You're alluding to we should check it?
Yes.
Okay. Making sure.
You probably got that one by now. I'm 99% half sure that we have no errors. Might we have errors? I mean, you know, like John was asking about the parameterization. Could I drop the negative? Could I have messed that up in some capacity? Of course I could. And there's no possibility I'm ever going to find it unless I check it. But the check is actually the easiest part. So let's start with negative 1, 1, 0. All right, so I get negative 1 plus 2 plus 0, that's 1. Negative 2 plus 1 plus 0, that's negative 1. Negative 2 plus 2 plus 0, that's 0. Huh. Is this good, what I have?
Yes.
Well, let's see. I believe it's exactly negative 1 times this, and that's lambda, and that's the eigenvector. So is that a good thing?
Yeah.
Right, crowd rejoices, but not yet. Minor celebration, right? We don't really get to do the full-out celebration until we're all done. We've got a small victory, right? This is the Cinco de Mayo. Everybody understand? Cinco de Mayo, that was yesterday. This is the small victory, but we didn't actually win the war, did we? Yeah. So we're celebrating a small victory. All right, second problem. Negative 1, 0, 1. Negative 1 plus 0 plus 2, that's 1. Negative 2 plus 0 plus 2, that's 0. Negative 2 plus 0 plus 1, that's negative 1. Is this in fact negative 1 times my eigenvector?
Yes.
Yes, it is. 2 for 2. What this guarantees now is I can solve this system. If I only got one eigenvector, by the way, where in the process would I know that I only got one? Anybody know?
In the equation.
Right here. If I had only gotten one row of zeros, If I had two linearly independent rows here, that would mean I would have only gotten one parameter, which means I would have only gotten one vector, which means I don't have enough vectors to solve this problem. That would be a problem, okay? That's not the problem that you're gonna see because you can't finish it, so that's usually not even asked. Yeah.
So the product of multiplying that matrix with the basis of the eigenspace should be a multiple of the eigenspace?
Yes, remember, what is the whole point? We're solving AX equals lambda x. That's where all of this came from to begin with. And we're just verifying that our particular eigenvalues and our particular choice of eigenvector solve that. If there was one number off anywhere, if these weren't the right eigenvalues or these weren't the right eigenvectors, this can't work. It's impossible. But because it worked, we know we're correct. Now we have one more to find.
5.
I'm gonna erase this. We've got this. I hate doing this, but how many were in my Calc 3 class? We did Green's theorem. Where did we start? Do you remember? You know, we started over there, and where did we finish? Over there, and I had to move the camera multiple times. Yeah, because I didn't want to erase. Yeah, the Green's theorem. And if anybody's ever watched my Green's theorem lecture when we were at home doing the online thing, I did that same lecture on the 3x4 whiteboard. People said they loved that one better. I had to erase the whiteboard like 30 times because I actually fill up all of these boards. Yeah, it's a big problem. But this one here, this is big, but it's not that much bigger. We're almost to the point where we can give an answer. So we're now going to do the second one, which was, I erased it. What was our next eigenvalue?
5.
5.
Positive 5?
Yes.
Okay, so we now want to do a minus 5 times identity and augment it with the 0 vector. So we're subtracting 5 now from the main diagonal. So negative 4, 2, 2, 2, negative 4, 2, 0, 2, 2, negative 4, 0. Well, none of these are particularly friendly, so I think I want this one to be my row 1. So I'm going to switch rows 1 and 3. I'm going to be lazy. Usually you write the instruction. I'm just going to say it out loud when I'm doing. Now, most people are told early on that a pivot has to be a 1. It's nice if it's a 1. It could be a negative 1. No, actually, all your pivot needs to be is a factor of the things below it, right? I just need the things below 2 to be multiples of 2. I don't need to make that into a 1. Yes, I can. It would be absolutely correct. I don't need to. You know, we're a lot of times told information that just doesn't make any sense. No, that's not a rule at all. Everything below the 2 is a multiple of 2. So I'm going to use a 2. I'm lazy. Why take an extra step to do the same thing? So negative, negative, the negative, 2 of those, 2 of those, 2 of those. What would that be? Negative 6? Does that look right?
Yeah.
No,
Or
hold
no,
on.
it- that,
I
that
like
top middle right one should also be a positive 6.
The top
The,
middle.
no,
right.
the middle right one, what's in 2 on that one, that should be a 6, I think.
So oh, you're right.
Yeah, 'cause it's
You're right. The negative of this. Okay, that's good. Now, I do want to make the middle row. I think I do want to have a 1 in there because I need to go up and down, not just down. I can go down, but remember, if you know you're going to parameterize, you want as many zeros as possible. It makes the algebra easier.
For the bottom row, you did 2 of the top and add, right?
Yes,
What about the middle there?
I negative the top and add it.
Yeah. The middle number.
0, negative 6, 6.
Sorry, the bottom row.
So 0, 2 of these should be 6, 2 of these should be negative 6.
Okay.
That's
I thought it was a 0 for some reason.
My 6s are not great, but yeah, it looks different enough for me. Okay, so let's how about take negative a 1/6 of this row?
Yeah.
Then make our life just slightly easier. Okay, now we'll go ahead. Now again, when you know you're going to parameterize, you don't have to go up. You should go up. Because you want as many zeros as possible. It makes your parameterization less taxing.
You switch the negative.
Did I screw it up?
You switch the negative in the middle row.
Well, no, I
They do one-
actually
never
chose
mind.
to
Okay,
be
never
one.
mind.
Yeah. I said negative 1/6. All right, so if I go up, negative 2 of these, that'll be 2, 0, negative 2, 0, 0, 1, negative 1, 0, and negative 6 of these, See, I want those additional zeros. It makes it easier. So now, you remember the rules of parameterization are pretty clear right now. The rules of parameterization, I think I just erased everything, but you guys wrote it down. I'm not going to pick x1 or x2 to be a parameter. That's a poor choice. Too much algebra. Always pick the one that's showing up multiple places. So pick x3. I could pick any of the three, but it's extra work if I pick one of the other two because then I have to solve two equations. I don't have to solve anything. So I'm going to let x3 be t. Then what's x1?
1. That's also T.
Just t. What's x2?
T.
Ooh. Like the way this one's shaping up. So, any vector of the form t, 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 or t times 1, 1, 1. Depending on your parameterization, how you did it, you might have -1, -1, -1. Would that still work? Yeah, it's a constant multiple. Any multiple of this will still work. So we will choose our x3 to be 1, 1, 1. And now we will check it. So 1 plus 2 plus 2, that's 5. 2 plus 1 plus 2, that's 5. 2 plus 2 plus 1, that's 5. And that's 5 times 1, 1, 1. Is that a good thing?
Mhm.
Yep.
Oh, yes. We have 3 eigenvalues, we have 3 eigenvectors. In a linear class at this point, we'd now come up with the matrix P. We'd find P inverse, we'd diagonalize, we'd do all these things. We can actually now state the solution to the differential equation if we want to do it in vector form. So I want to do both forms. I actually want to tell you what is the function y1, what is the function y2, what is the function y3. But let's start with the vector form first, because that's actually the first thing we're going to see. Yeah, John.
Why wouldn't we, or could we just like plug that original matrix into the calculator?
When you said that original matrix,
Or
which
A minus 5i matrix. So that plug that matrix into the calculator and then row reduce, and then just skip all that math stuff and then get to that.
yeah, but you still want to be able to get to that.
Okay.
Because you're not going to be able to do that on an exam. And here's the funny thing. People say, why don't I just use my calculator to find the eigenvectors? Good question. Let me know when you can do it. Why is it an impossible thing to do? It's impossible to find eigenvectors using any form of technology. It's real simple. Technology will help you when there's one answer. How many answers are there?
Infinite.
Infinitely many. And it can't simultaneously give you infinitely many solutions to one question. That's why I said all answers are correct, but there is a most efficient choice. See, do you all agree that 1, 1, 1 is probably the most efficient choice? But every integer multiple of that is a good choice, except 0. Could I have 1/2, 1/2, 1/2? Sure. That's not as good a choice if I'm trying to diagonalize and do other things. I'd rather use integer values. You can use any multiple. The problem is technology can't give you this because this was a choice. We chose the base A vector as our basis, but there's an infinite number of choices there. Now, the calculator can row reduce for me as long as my first pivot isn't a prime number. Other than a prime number that isn't 0 or 5. In other words, my first pivot's a 7. What's it going to give me in every position? Decimal approximation. The calculator cannot store fractions. Anybody's written a program, you know this. It's integer or it's real. It stores decimals. And if your first number is a fraction that doesn't have a terminating decimal, this process doesn't work particularly well. If you guys have ever done your did you guys ever do the upper triangular, lower triangular factorization? Yeah, there were pitfalls. If your pivot was a 0, it's actually impossible. Yeah. So there are certain conditions that even technology can't get past because it has to deal with a number in the position. You don't. You can rearrange to your heart's content. Now, we have all the answers. Let's go and answer this question now. So we're going to do it in this form first. I'm a linear guy. I don't like this form because y1, y2, and y3 are functions. There's no vector associated with the question. But at a convenience, it's really fast to give the answer this way. So this is going to be C1 times something times e to the something. I'm gonna be purposely vague. And then the next one's gonna be plus C2 times something times e to the something, and then plus C3 times something times e to the something. So let's start with e to the somethings. What were my eigenvalues?
1.
Was it 1?
2.
Was it 1 or negative 1?
Negative 1.
It was negative 1, and it had multiplicity. So it's going to be negative t, 5t. What was our first eigenvector?
Negative 1, 1, 0.
What was our second eigenvector?
Negative 1, 0, 1.
And the one we just did was 1, 1, 1.
Yeah.
This is a viable solution to this problem. But I still don't know what y1 is. I don't know what y2 is. I don't know what y3 is. But can I glean that from that easily? Yeah, that's easy. The C1, C2, and C3 are actually important because they can be any real numbers including 0. Because that would actually work.
Before, when we had multiplicity, we had to multiply the e's by a value of t. Do we not have to do that
That's
here?
because that solution, that one wasn't diagonalizable.
Oh.
The author was kind of cheating because your final answer can't actually have a t to the t. It can only have e's. That's what I'm saying. That it's kind of fudging the answer because it isn't of the form. It doesn't work for this.
Okay.
That's why I wanted to do that problem to show you guys that that's a goofy looking answer. Why? Because there wasn't a second eigenvector. So the answer doesn't have this form. You can't go directly to that answer. You can't diagonalize the matrix, which means there isn't a unique solution. If I gave you initial conditions, it wasn't actually solvable. But every Diffie-Q does that because they got an answer. It's just not really going to work. Why? Because you only had 2 eigenvectors, not 3. You got to have 3. Okay. Give me a better, well, not a better. If this were linear algebra, this is not what our answer would look like. And if I wanted to check this through differentiation, this is definitely not what the answer is going to look like. But telling me what y1, y2, and y3 is, I want this to be trivial. Because when I ask you this question, either form of the answer is absolutely acceptable. But I'd far rather you know how to do both. Because then you can choose, because it's a context thing. Right? What are you using the answer for in the next step? If you need it as a function, then you need to tell me what y1 is. So what's y1? Just go across the top. Negative C1, negative C1, e to the negative t, negative C2, e to the negative t, plus C3 to the 5t. Everybody got that? And then I just continue. This is a piece of cake. So then it's C1 e to the negative t, plus C3 to the 5t, nothing in the middle. And then the last one, nothing here, C2 e to the negative t plus C3 e to the 5t. C1, C2, and C3 can be any real number, including 0, and these will work. Now, why can they also be 0? Because if the c's were 0, then my y's would actually be 0, and that actually would work. If all my y's were 0, then the derivatives would be 0. And yeah, that's kind of a boring answer, but it still works. It's not the one you're going to do. Will you ever know the values of the c's? If I have initial conditions, which strangely enough, we hardly ever do on this type of problem, because the initial conditions are not part of the solution. It's just a little bit of remedial, heck, it's not even algebra, it's arithmetic at the end of the problem where I find them. That's why I don't like to concentrate on those. It's not that important. In Calc 2, we learn all these methods of integration, but we rarely ever do a definite integral. We did those in Calc 1, but in Calc 2, we're interested in getting the right antiderivative. The definite integral means, okay, now plug a number in at the very end of the problem. That's not calculus. That's arithmetic. So we don't focus. But then in Calc 3, you rarely do an indefinite integral. Your answers are always numerical because you're finding a volume or a surface area or a work or something. But we already know how to evaluate. So part of the reason you do that is so that you know your answer actually made sense. One of the questions that just came up in my Calc 2 class, they're doing arc length. And the person said, did I do it right? I go, I don't know. Is your answer positive, negative, or 0? They go, what do you mean? I go, because it had exponentials and sines and cosines. So they plugged it in on the calculator and said, well, it's positive. They go, well, that's a good sign. And they said, why? I said, you're finding arc length. 2 things it can't be, negative or 0. And it dawned on them, oh, you're right. That's all I had to do. I go, well, you could still have an error, but at least now your answer makes sense. If you told me the volume or the surface area or that person's age or height or weight or how many units they're carrying and you know how fast they drove on the freeway, if you gave me negative numbers for any of these, it probably doesn't make sense. Right? So sometimes it's common sense. This is as big a problem as you're going to see. I want to show you one more, an evil one. Okay, not the problem you're concerned with, but this is where diffie-q really takes a right turn from linear. In linear, the king of the hill of the matrices is something called a Hermitian matrix. Yes. I just did a symmetric matrix. The Hermitian matrix is one where the conjugate transpose is the same matrix, which means your diagonal entries have to be real. And in the Hermitian matrix, you have complex numbers all throughout, but your eigenvalues, we prove it, the eigenvalues are actually real. And in real life, you can't deal with problems that you have complex eigenvalues. You don't actually have application. You can have complex eigenvectors, strangely enough, if your eigenvalues are real. What if the eigenvalues aren't real? So I want to walk you through the process. This is not the most important problem. This is a problem that can come up. It's more likely to come up in an upper division version of the class, and it's not something that I want you to emphasize and make it overly important. What we just did is consider a pretty important application. A lot of folks will say it's the most important application of linear. I disagree with that. I think there's another one that's more important. But this is an important application of linear when applied to differential equations.
Doesn't the rotation matrix have complex eigenvalues when you shift 90 degrees? I believe it has.
Not necessarily. Depends. Because all you're doing is you're doing sines and cosines.
No, I mean only when it's a 90-degree shift. I believe it's I and negative I as eigenvalues.
No, but I'm saying is you're only multiplying by a 2 by 2 with sines and cosines. It's actually, you're not really doing eigenvalues and eigenvectors. You're just doing a simple multiplication. This is one of the things I don't do this anymore. I used to do this at the end of chapter 6 in the linear book. I would show you how to do a rotation of axes, and then you go, in Calc 2, it took me a month to do that one problem. You're saying I can do it with a 2 by 2 matrix? Yeah. But you don't know matrix algebra in Calc 2. Yeah, turns out all that work was a waste of time because there's a really, really, really easy way. Once you find the angle of rotation, you just multiply it by a 2 by 2 matrix. It's like, oh my gosh. But as you know from Calc 3, you never do rotation of axes. So it's really a one-time thing in Calc 2, so don't dwell on it. All right, I want to do this problem. I don't care about the final answer as much as the process, because this one's going to be very different. And in fact, I may not finish because I want to make sure we get to the review, okay? So let's start the process. This is 2 by 2, so no matter what, it's not going to be terrible in terms of the algebra. So when I do the a minus lambda I, that's going to be, I'm just going to go right to it, just save some time. So 2 minus lambda, negative 8, 1, negative 2 minus lambda. Y'all with me? Now, if I just randomly, heck, make it easier. I want everybody here to just make up 10 2 by 2s. Just make anything up. Put any numbers you want. Keep them integers just to make it easy. But you're just going to make up anything you want. And now we're going to find the eigenvalues and all that kind of stuff. Do you know what I can tell you with almost absolute certainty? Half of all of our problems are going to have complex eigenvalues. Why? Because in the 2 by 2, isn't my lambda going to be a quadratic? And exactly 50% of all quadratics have complex roots. So if you just randomly made up 2 by 2s all over the place, half of them are going to have complex roots. So complex roots aren't rare. They're going to happen half the time. But we tend to concentrate on the ones that have the real roots. And in fact, to make it even easier, we concentrate on the ones that have integer roots. Yes, that's completely artificial. But we're learning the process. We don't need to be killed by the complexity of the numbers. So when we do this guy, what do we got? Negative 4 minus 2 lambda plus 2 lambda minus lambda squared plus 8. Does that look right? Well, that's beautiful. Look at that. Oh, it's so nice. So this is lambda squared. Whoops, sorry, that would be, that's plus, sorry. Boom. Negative plus plus. Okay, good. So this is lambda squared plus 4. Cool. And that equals 0 when
Minus 2i.
ooh. Ouch. Yeah. In fact, that's not the worst one. I mean, it could be worse. It could be 2 plus root 3i or something like that. No, this is just 2 plus or minus 2i. That's actually not that unfriendly-ish. Okay, so. So those, how many remember taking a determinant of a complex matrix? Did anybody ever do that in your, you would have done it in my class because it's chapter 8. But to take a determinant of a complex matrix can be kind of messy because you're multiplying the complex numbers. To do row operations on a complex number is really nightmares. What multiple do I take? And when I do, I can give you something where the rows are multiples, but you don't actually see it because they're complex conjugate kind of multiples. And it can be really messy. And it's not always obvious. So let's start with the negative. So I want to do A plus 2i times identity matrix augmented with 0. So I'm adding 2i, okay? So this is going to be, I'm adding, let me go back. My A matrix was 2, 1, negative 8, negative 2. So now this is going to be 2 plus 2i, 1, negative 8, negative 2 plus 2i. Now, if I did this right, those rows are multiples. This is what I'm referring to. Those rows are obviously multiples. Everybody can see that, right?
Just multiply it by
Would you say it's not entirely obvious that those rows are multiples? So what am I going to do? Well, how about we do this? I'll write it out. I'm going to take the negative of 2 plus 2i times row 1 and add it to row 2. Okay? So I'm not touching row 1. So when I take the negative of this and add, okay, that's obviously 0. Now I'm going to take negative 8 times negative 2 minus 2i, and then I'm going to, did I do that right? I'm sorry, negative, I said that completely backwards, my bad. I'm sorry, I want to switch the rows first, sorry. I was doing that part in my head, that was evil, sorry. This is what it should be. Okay, 2 plus 2i, negative 8, 0. Now we'll take the negative of 2 plus 2i times row 1. There we go. I don't know what I was thinking. That was crazy. Okay. So that's a 0. Now I'm going to take the negative of 2 plus 2i times negative 2 plus 2i, and I'm going to add that to negative 8. Ugh. You agree that's kind of yucky? Okay. So that's negative 4 plus 4i minus 4i plus 4i squared. What's plus 4i squared?
negative 4.
That's negative 4. And I have the negative of that and then minus 8. Okay, so that's the negative of negative 8 minus 8 is in fact 0. So that means we did it right. When you're working with complex matrices, seeing something as simple as 2 rows are multiples of each other is not always trivial. These rows are actually multiples of each other. But until I do it, I'm not absolutely sure. So, whew, I got it to here. Now we need to parameterize. I'm going to go the first half of the problem. I don't need to do the second half because the second half is going to be exactly the same thing, and then I want to write our answers in the vector form like we did before. So let's go ahead and parameterize this. Now you guys know the rule of thumb. When you have 2 choices and one of them's a 1 or negative 1, you always pick the other guy as your parameter, right? You always pick the more complicated. So I will clearly choose what? x2 to be t. Then what will x1 be? Be the negative of this,
2 minus 1.
t. And it's really easy to check. So if I take 1 times that, and then that should add to 0. So that means any vector of the form 2 minus 2i times t plus t, comma t, which equals t times 2 minus 2i 1. Can I go a little further? Like maybe split the real and the imaginary up? What do you think? That might be useful. So 2, 1.
Negative.
How about plus I times
One.
negative 2, 0. Did that work?
Yeah.
So is everybody cool with that so far? So I'm going to choose this as my eigenvector. But what if I wrote it like this instead? Remember, a vector can always be written as a column matrix. And when we went to check them, didn't we do them as column matrices to do the check? But in this case, that might be more efficient to write it that way, because remember, we're also going to write the vector form of the solution. So there's my eigenvector. I said I'm not going to finish the problem. I'm just going to do the first half, because the second half is identical. I'm going to do the same thing with the other eigenvalue. I'm going to parameterize, and we're going to get something that looks like this. Then we're going to put it all together. So here's what I want to say. This goes with the first eigenvalue. So if I say C1 e to the what?
Negative I.
Is this one's negative 2i, I believe?
Yeah, I think negative 2i.
And by the way, and this could be blah, 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 e to the 2i t. Everybody sees that, right? We have the other stuff. Everything I said is true. Everything I said is correct. Are you happy with that answer?
No.
You shouldn't be. Why?
Sines and cosines.
Yeah, I have an by the way, the I in front of the vector, you can't do anything about. That's there because I have complex numbers. But I have an imaginary exponent. I really need these to be real functions, don't I? Oh, and that's the big twist. Everything I've done so far, I would say is manageable. Icky, but manageable. But we agreed this is not an acceptable final answer, so I need to tweak that. E to the negative 2it.
Cosine of 2t.
Well,
Or negative
let's
2.
first things first. Oh, cosine of negative 2t plus I
Sine of negative.
sine of negative 2t. Now if I want to do it in terms of 2t, what would it be?
Cosine of 2t.
Even function.
Minus I sine of 2t.
Yeah, that'd be safer because I don't want to lose. Oh, so now what am I going to do with this? It's going to go here. So now I have all of this times cosine and then minus I times all, but the things will combine. Now here's my point. What's our other eigenvalue?
Oh,
Isn't it positive 2i? So in the end, aren't I also going to get another cosine 2t plus I sine 2t, but with two different eigenvectors? So what you're going to do is distribute and regroup, not by that, but by cosine and by sine. Is there a lot of algebra there? Oh my God, we have more algebra left in the problem than we've done so far. So once again, when I put this in here for this guy, I now have this times the cosine, this times the cosine, this times negative I sine, this times negative I sine. I now have 4 terms. 2 of them are sines, 2 of them are cosines. I do the exact same thing with 2i, and it has 2 eigenvectors. I do the same thing, but in the end, then I gather the sines and the cosines. But the beautiful thing is, I can make all of my coefficients real. The reason is I'm going to have, like, C1 plus C2 might be one coefficient. The other one might be I times, C1 times C2, and I'll just call that, I don't know, C3. Because I times something, I can call anything. Is there any limitation on the coefficients in terms of real or complex? No, not the coefficients. They always could be anything. We just never think of it that way. Because it's still just a number. Whether it's a complex number or a real number, it's still just a constant. And so it doesn't affect differentiation or anything else. This problem is long. This problem is no way around it. So I wanted to do the first half. Okay, I actually have posted notes on this, but it's for a 3x3. I don't know that you want to look at that. You might change your major. Yeah, I probably should. The posted notes I probably should have made a 2x2. I did it as a 3x3, and the reason I did it was actually several years ago, many years ago. I was subbing for somebody, and they were going to be out an extended period of time, but then they confided in me they had never actually taught any of this. and they were kind of worried that they were going to be hopelessly unprepared. Plus, they were also out, and they said, "Could you go ahead and cover?" It was like the last 2 or 3 weeks of the course. So I said, "Sure," but I wasn't teaching DiffyQ currently, and these people had never seen any of this. So I figured, you know what? Let me just go ahead and write it up, and then I can give them handouts. It'd be a lot easier. This is even before Blackboard. This is a long time ago. So I wrote it up because I think the teacher wanted them to do a 3x3. And now I'm looking back on, it's too big. This problem right now, we're halfway done, and you see how much more there is to do. It's not hard. It's just really long-winded, and there's no shortcut. But the answer is ugly, but it still follows the form of everything else we just did. Okay. Now, is anybody here good at this? Maybe I'll get lucky. I probably won't. If I have, can somebody come just give it a couple tries? Usually, if you make a mean look, for some reason that always seems to work. I'm going to bring up the practice. Oh, did you get? There we go. I have a person in my stats class. No matter how many times I try, she goes, "Let me try it," and literally she's this far, and it works. If she does it, it works on the first try. If she makes a motion towards the board, it works. The board is terrified of her, I think. Okay. I'll change the lights in just a second. Yeah, I don't want any ambiguity on what's going to happen. Hopefully sometime you guys will designate the donut person this time. I think somebody totally messed up last time and no one brought the donuts. And, I mean, you brought the streamers and those things that you blow on them that make noise. What are those called?
A kazoo. No, I
No,
don't know.
the really annoying things that at graduations everybody does, and they're usually sitting right behind you. You know those people? Yeah.
Yeah.
Some of you might have been those people. I don't know. Okay. I could just do exam 3 key, right? Should I just do that instead? Save us some time. Beautiful. Okay. So I want to talk about the nature. All right. So the exam only has 2 parts, right? Power series and Laplace. But within the parts, there's a lot of detail. You do not have to know the power series representation of any function. Please don't write down e to the x or sine x or cos. When have we used that? We haven't. Don't. It's the space you might need for something else more important, like Laplace stuff. No, I'm going to give you a power series, and I might say solve it, but if I say solve it from beginning to end, it's going to be low level. So it's less likely I'm going to have you solve it as one problem. The problem I'm far more likely to ask you is, this one's pretty easy because it's first order, but right here, this part right here. No, that didn't work. One of the things I may ask you is, given the power series, give me the recursion for the coefficients. You can't start with that. You have to group things. You have to get everything right, starting and having this. You can't answer the question until you get to here. All of the algebra and the problem's right here. Now, if I ask you for the recursion, would you agree that's probably the most important thing? Because now I can find the coefficients. Whether there's a pattern or not, it's not important. If there's a pattern, hopefully you'd see it. If there isn't, don't worry about it. But the recursion, that's going to be the question. I might just say, given this, give me the recursion. A second question might now be, solve the power series. And you say, well, I've already got the recursion. Now I just need to crank out some coefficients, see a pattern, or not see a pattern and put some dots. But in other words, this power series becomes 2 completely separate, independent questions. It's too much for one question as far as I'm concerned. There's just too much there.
So you're saying like one question could be just fine, like C n plus 1.
That's one question, and then the second question is now finish the problem.
Okay.
Because I think all of you can do all parts, but if I'm letting you choose problems like I always do that are equal worth, no one's going to choose that one because it's twice as long. I mean, literally it's twice as long, but if I make it 2 problems, oh, it's 2 of my questions. Now I might do both parts. The one thing you can't do the second half of the problem only.
Just saying, you know, you can only do the second half if you did the first half.
Will the exam be as long as the practice exam?
Well, yes and no, but you're not doing every problem.
Right.
You always have choices. So this is really the same thing. This one is probably more represented because it's second order. I'm going to ask you to solve a second order power series. Okay? So again, you got it to the recursion, boom. And then in this case here, this was kind of wimpy because it ended up just being a simple polynomial. But
Can I stop this? Is the
no, let's keep it going.
And then I had another question.
Yeah.
If we see from the beginning of that problem that you're looking at that y prime is 0, and then we get to the recursion and it's like an a plus 2, can we just say that
Well,
all of the odd ones are
Well,
just going to be
say
0?
it first. Say it first. Say A1. In this case, you could say A1 is 0. The A3 is a multiple of A1. Boom.
So we don't have to do like the
but
odd pad.
but the A1, even if you get that thing where they're all 0, the first one's not always 0.
Yeah.
So be a little bit careful on the starting. That's what I'm saying.
Okay.
Don't. What if I said A prime of or y prime of 0 is 1, but then when you got to the recursion, all the odds end up being zeros,
Yeah.
except for the first one. Have we had a problem like that?
Yes.
Yeah, and unfortunately, some people made all of them zeros when it was no. The first one wasn't. I'm just saying, just be careful. Yes, you can save yourself time.
Just because this one was y0 is equal to 0.
Yeah, as long as it's separated odds and even separately.
Okay. Yeah.
What if this is consecutives?
Then no.
Then it's even easier.
Yeah, because all of them after.
Everything after would be 0. Yeah. So take advantage of a pattern if you see it. Yeah, Patrick.
When you're summarizing the series and you have to put the constants in front of the series, right there, 2C2 plus 8CO.
You're talking about this line right here?
Yeah, since they both they add up to 0, can you put 1 to the other side and say 8CO is equal to negative 2C2? Oh, okay.
Yeah, right here. Yeah.
And why would you do that?
To prove.
Because are you going to plug it into the equation like that? Or
Well, because first of all, they're not both 0 that way.
oh,
Gotta be a little
okay,
careful. And also, this, I can see, this is an observation. Stop here. Now go to the recursion.
See, plus
Is it up there somewhere?
Yeah. It's the row right above it.
Yeah. Above.
So within the recursion, is it still consistent? That it would still be the same thing? That's important. That it's not often that you have stuff in front, but you sometimes have stuff in front. And the stuff in front has to add up to 0 because remember, all coefficients have to add up to 0. If your recursion and this contradicted itself, we'd have a problem. Because that would mean I'd probably have more trust in this because that didn't require any work. That required a little bit of manipulation. That's one of the reasons you really want to do that, because if it agrees with the recursion, I have complete faith that I did the recursion right. There's no way it's going to agree with the recursion and I made a mistake on the recursion. You're never going to get lucky like that. So does that make sense why you would want to do this?
Yeah, because it's CO pops up in the recursion.
Okay. Somebody, questions?
I know it's not really, it's probably not a big deal, but throughout all of our notes, we've been staying like AN.
It doesn't matter. I go back and forth. Because in some classes I did it with C's because the textbook we were using at the time might have had C's. Some textbooks have A's. I just keep the same letter throughout the problem. That's all that.
Okay.
You know, I laugh because some of you like using B's. Some of you use B's on everybody. I don't care. Just don't be switching midstream.
What is the upside down A?
For all.
For all.
Okay.
That's called the universal qualifier. What's the backwards capital E called?
The capital what?
The backwards capital E goes with that one.
Oh, for every element?
The other one's.
Oh, wait, never mind.
The existential qualifier. That's there exists.
There exists a.
This is weak. This means there's at least one, and that one means it's always. You know, they're kind of the extremes. But those are math symbols that we use a lot. Okay, let's move on. What else do you need to be able to do? Singular points. Most of you were very good at this, but some of you had some misconceptions on how to do it. At what point in the problem are you identifying your singular points?
The beginning.
The very first step of the problem. You're dividing through later to figure out the type of singular point. But if you divide through and everything cancels, that doesn't mean it's no longer a singular point. And that's the mistake some of us made when things canceled. Oh, it's no longer there. but that'd be like a removable discontinuity. It's still a discontinuity. So right now, my only singular point is x equals 0. Now I just have to determine whether it's regular or irregular. So how do I do that? If I'm asking for what type it is. Here I asked you for something else. If I was asking you the type, when you divided through, it showed up once here, it shows up twice here. Does that make it regular or irregular?
Regular.
Regular. That's okay. That's why we can continue this problem and actually do the whole thing. Now you're doing it using the initial equation version. Yes?
Can you reveal us when to use Cn xn plus r and
Oh,
when
yeah.
Cn xn?
Because x equals 0 is a singular point. That's the right question. Let me go back to the previous two problems. You have a 1 in front here. You have a 1 in front here. I have an x squared in front here. X cannot be 0.
Oh,
0 is a singular
every
point.
time with the x.
It's whatever makes that 0. What if instead of x squared in front, it was x squared minus 1? Then 1 and negative 1 would be singular points, but 0 would be fine, and then I just do it the old-fashioned way. It's only when x equals 0 is a singular point that we do the x plus r thing.
Okay.
That, everybody got that? That's the right question right now. Because if I don't know that, I'm going to attack this incorrectly. Now, the initial equation, we did a lot of work, we got this thing here. But once you have, go back to the step before the initial equation. Okay? I have a constant term in front of x to the r, I have this. It's a lot of gobbledygook, okay? My recursion is coming from here still. It's still coming from here. So once I found the roots of the initial equation, I now wanted to solve the differential equation. Again, this would not be one problem. So the way I would ask this problem is, find the roots to the initial equation. Now I will say take the bigger or the smaller. I won't do both. I'll just say take one of these roots and now solve that differential equation. So in this case, let's say I wanted you to take the smaller one. So now you're going to solve the, well, how do I do that? I go to the recursion. I got to save some time. But you would write your recursion with, it would have n's and r's in it. But then I replace the r with this value. So now it just looks in this form. And now it looks absolutely convenient, familiar, and everything else. So in the initial equation, it's finding the roots, then solving the problem. But you really want to get it to here because then your recursion is sitting right there. When I'm asking for the roots in the initial equation, I'm not asking for the recursion, but the recursion should be there because otherwise you won't be able to do the second half of the problem, which would now start with the recursion as your first step. Because you've already got everything right there. This one is a little more work because you've got extra terms. And here's the other thing. When I'm doing the sum, I'm sorry, I got to go down a bit. Notice that when we did the first derivative and the second derivative, they started at 0, not at 1 and then at 2. The reason? In the previous ones, it was just x to the n. So when I moved an n in front and I'm starting at 0, n is 0. But now it's n plus r in front. N can be 0. I wouldn't be starting at 0, I'd be starting at r. That's why when you do the first and second derivative, your sums actually start at 0 on both of those.
And you said we use this technique when x is a singular point.
When x equals 0 is a singular point.
Okay.
Okay? So let's move on. Now,
Sorry, that was the problem that, like, this question was the only one I wasn't able to figure out after figuring out the roots of the initial equation.
Okay.
I just have no clue, like, how to continue from there.
okay, let's do this. Let's go to the recursion because
Yeah.
this is important. We did this as a day. But isn't that the problem with our exam? We did 7 concepts, we did 7 days, we did them, but none of the concepts were short and sweet, right? All of them were kind of huge. So you found the roots. Hold on, it's right behind me.
One instead of the half.
Hold on, let me find the, let me write the recursion down, okay? So I've got n plus r, 2n plus 2. This is where you gotta be really careful when you're gathering these. If you have an error here, this is gonna monumentally fall apart, right? I'm taking this right from the sum. Okay, plus cn plus 2.
Is it plus or
Oh,
minus?
minus 2, sorry. This right? I'm just copying it right from the summation.
Okay, so this equals 0.
So I now want to set this equal to 0, which means if you want to do this before you plug in your roots, this is totally okay. So you'd say Cn equals the negative of C. Actually, I usually like this. I usually like to write it next to. I think it's easier to read. So this would be 1 over all of this gobbledygook. Okay. Now, here's where you'd say, okay, now pick one of your roots. You want to use one? Okay, let's use positive 1. Less ugly, I agree. So we're now going to use the root r equals 1, and let's say that's the problem we actually want to solve completely. So then what's Cn? That would be n plus 1.
And minus 2.
This would be 2n plus 2 minus 3, and then still plus 1. So I'm going to multiply this out. 2n squared minus n plus 2n, oops, minus 1 plus 1. Oh, so what have I got? N times 2n plus 1?
Yeah.
Sorry, this is a little bit cramped. Is that scary? No, that's pretty friendly. Can you see what it is? Do I have that somewhere on here? Oh yeah, I do have that on here. That's the next step I have on here. Okay. I don't think you can see it clearly. Let me.
So you had +1, but here it's -1?
I'm sorry, say it again.
You had in here, it was 2 and -1, and there you got 2 and +1?
Well, no, I multiplied it out, add the 1, and then back.
Yeah, I was just comparing the two. You had like...
Oh, did I write it different up there?
No, that's the next one.
Yeah.
Oh, that one. Oh,
Yeah.
sorry, I was
I
looking
think
at
I
CN.
have, this is somewhere
Yeah,
on here.
BN.
Yeah.
It's
Yeah, you
BN
were doing the
instead.
BN.
Yeah,
Okay.
for R equal, that's, Mateo was asking me to use the 1 instead. It's,
I see.
Okay, so I see you got 2 recursions.
But do you see what I did was, I have the recursion in the summation sitting right there, but the moment I replace R with a value, all of a sudden my recursion is going to come really small because it's, right, you don't have all these extra variables in there. It's not that bad at that point. So now you would say, let me solve this differential equation that has this recursion. And then I'd go through, hopefully I'd see a pattern. If I don't see a pattern, what do? Hey, what do you know? No pattern.
It says right there C1 equals 0 immediately after you found those R's, so I was just like, I got very confused at that point. Like you said, R equals that, R equals that. Thus C1 equals 0.
Where are we? Because, okay, go to here. This whole coefficient has to equal 0. Regardless of what C0 is, that whole thing has to be 0. We'd really rather C0 not be 0, because then that would mean the first term is 0. And then the next one also, where's the next one? This also has to be 0. But R was either a half or 1. Do you see the problem? 2R plus 1 times R is never going to equal 0. Oh, that means the C1 had to equal 0. But over here, this product equaled 0 when R was a half or when R was 1. C0 was not 0. The 0 came from here or from here, but once I have those two R's established, neither one of those R's would make this 0. You with me? Therefore, the C1 has to be 0, because remember, every coefficient along the way, this whole coefficient has to be 0. That's where the recursion comes from. So that's not a trick. I'm just simply reading. So the coefficient in front of x to the r, the entire thing is 0, which comes from the two r's. The entire thing is 0, but it didn't come from the r, so it had to come from the C1. Does that make sense? What if? What if instead of, what if that was a 2r minus 1? Then the 0 would have come from here, not from the C1. And then I would have kept going with the C1. Right, because the value of r was 1/2, was one of them. Okay? This one is gnarly. That's why, again, it's broken up into pieces. Now, let's get to the Laplace stuff. You have 4 that you now know. You know the exponential, you know the sine, the cosine. Do write them down. The sine, the cosine, the k, and the s on top, people still will get flip-flopped because you know they're almost identical. And when you're staring at it, you go, no, write it down. And you know t to the positive integer n. Now, I gave it to you on the first day. We actually derived it last time and we realized the derivation was kind of complicated. Now, what do you know also? You know the exponential shift. So if you have a Laplace transform of e to the something, you just get to shift it. You now know the derivative version. If you have the Laplace transform of t, and by the way, I won't ask t to a large power. T to the 5th power, 5 derivatives? No. I'll give you a t. If it's a really simple one, I might give you a t squared. You're not going to take a million derivatives. That's not the point. Right? So you know every version, and then the only other thing are the unit functions. Okay? You know how to write those. And again, you have a formula. Now, the going forward is not the hard part. The going forward is pretty much slam dunk. It's like in Calc 1. My first Calc 1 test is limits and derivatives. And they get to write down their derivative formulas, and probably half the test is just take the derivatives. So you're going to have some product rule, some closure rule, simple chain rule, the sine of x squared, that kind of stuff. And I will have people every semester miss every single derivative. It's hard to get no partial credit. And they got to write down all of the derivative formulas. How do you miss? I will actually ask the derivative of e to the x.
Some people don't know.
And they get to write down the derivative of e to the x on their formula card, and they'll still leave it blank. And I'll go to the class and say, guys, you should have got 60% just because you wrote down the derivative formulas. You should have got 60% right off the bat without having any concept of calculus. You can't leave blank when you get to write down the formula, and all I'm asking is the derivative of sine x or derivative of cosine x. But that's because they don't practice. Some never practice. You get to write down the Laplace transforms. I'm going to ask you for them. You don't have to integrate.
That's why I say you got to give them some homework. You need to practice.
Well, that's what a textbook is for. That's why the textbook has tons of practice. Now, the biggie is not the Laplace transform, it's the inverse. Now, if you can go forward, you can go backward. You already know that. But now you have to recognize things. You might have to complete the square in the denominator. You might have to do a partial fractions decomposition. You know you're going to have certainly low-level versions of both of those. Okay? Are you going to do any integrating? In fact, have you done any integrating on anything?
Yes.
What did you integrate recently? Well, I integrated like gamma function
for
stuff.
problem problem 12.
Yeah, I think I asked a bonus question-ish where I asked you to derive.
For the stepwise one, would we need to integrate
You
for
can
that?
use unit function.
Technically, no, this is
No.
unit function.
Oh.
Yeah, this would be unit function. No, this would not be the one. The first question on the 7.1 quiz, when I gave you a piecewise function and I asked you for the Laplace, oh, you had to go 0 to 2 and then 2 to infinity. That would be the extent of an integration, but that's yeah, it's an improper integral. Yeah, it might be an integration by parts, but it's a one-stepper. And I think I did it with an exponential function, so it wasn't a complicated one. Everything on here we have done. Now, this is the one that gives people more trouble, is one of this nature, right? The halves, because there's a formula, we derived it, but it's not something you've used a lot. So, halves only. And by the way, I want you to do the Laplace transform of, t to the 111 halves, Okay, then I got the 109 halves and the 107 halves, and I'd probably limit it to single-digit halves. How's that? You either know how to do it or you don't. I don't want it to fill up a page. Okay. There's a tendency, though. Tell me the error. Tell me the error right here. Anybody know what it is?
Oh.
3 halves. Yeah, that's the error. You've got to write down the gamma function formula. You have to write it down, but not with halves. No. Write it like this. What is it? Alpha. Write that down. The error, and it's an unforgivable error, is we have the wrong coefficient in front because we're thinking factorials. 10 factorial is 10 times 9 factorial. But here, gamma of 10 is 9 times gamma of 9, not 10. So that's where we get in trouble. So please, write that one down. That's not an error you can afford to make.
For this problem, when we were having this lecture, you mentioned that this works for -1/2 as well, but I don't think we did negative.
Oh yeah, I remember that.
Well, because the gamma function, or the t of -1/2 is the gamma function of 1/2.
Yeah.
We did the integration. I think we derived it.
Yeah.
If you go back to the actual hideous integral, remember, and then I used that really weird substitution. I said let t be u squared. And now you had u to the -1, and then it canceled. If you go back to the notes and how we derived it, the derivation I did the derivation for t of -1/2. We didn't do any practice problems because t to the -1/2 was the starting point. T to the -1/2 is the gamma of 1/2.
Oh,
That's why. And then the rest of them we use the recursion. That's why I never did that in practice, because there was no place to go. It died there because we started there. Let's see. Like every other test, and by the way, Deshante, I think this is the same question they had on the quiz, wasn't it?
Yeah.
Number 10.
It was a variation.
The question was for how do you attack this problem? I don't care if you did it right or not. I want to know that you could repeat what you did. Not that you went around the block 2 or 3 times, filled up a page with writing, and I eventually got the right answer, but do I understand what I did? When it's t to the first power, I think the easiest way to do it is to do your Laplace transform for the other stuff, and then just take the derivative. Yeah, I think that's just easier. There are other routes, but I think this is the most straightforward route possible. Now, the form you leave your final answer in. The numerator simplifying, things combine, I simplify. That was the question we had earlier. But if you left it right here,